So let me also start by thanking the organizers for this wonderful meeting at a very exciting time in the field. So I'm going to discuss some work with a broad view that goes back to 2008 but continues to the present for reasons that we've been seeing. I want to highlight my collaborators, in particular Westphal and McAllister, and recently Race, as well as these other guys. Also early work included works by Caliper, Sorbo, Lawrence, et cetera, as well as stimulated by BICEP, a lot of progress in the subject more recently. If you want reviews, there's a nice new book by Bauman and McAllister, and some notes that I've written recently as well. So as we've heard, BICEP2, with input from other experiments, which will continue to operate, made a truly tour de force improvement in sensitivity, measuring B modes at a level that is extremely interesting. First of all, it's consistent with the basic level we might expect from inflationary quantum perturbations, quantum gravity perturbations, which of course is uncertain in terms of the amplitude, but it's getting into a very reasonable range for that. As we've heard, it could also be consistent with foregrounds, which are not well understood and are hence rather uncertain and complicated. So there's been a lot of discussion, but I can just summarize it here. This is the score. We're in the third month of play, and it's basically, I can't believe I'm the first World Cup joke person in this strings. Thought it was more of a tradition. So we're in the third month of play. It's basically n to 1 in favor of primordial, where n can range from 2 to 10, depending on exactly how they analyze the synchrotron in that frequency curve. Okay. So my outline is going to be a quick review of the implications of this in general for quantum gravity, then come to string theory and talk about the simple mechanism we have there for large field range, which comes along with an underlying periodicity, an underlying discrete shift symmetry. I'll talk about some new examples in a broader phenomenological range that they exhibit. And finally, discuss one of the things we're doing now with these collaborators, where we have a deadline to produce reasonable oscillatory templates for the next round of CMB. So let me start with the big picture of this issue. So as Matthias reviewed very nicely, and I'll also review, we get a relation between the tensor to scalar ratio and the range of the inflaton field during inflation. And there's kind of a bottom-up prejudice, which is a bit of a straw man, but still worth keeping in mind, which I put on the left panel of this slide, which is to just say from the bottom up, we really don't know what quantum gravity is. I mean, we all know what it is, of course, but but we don't from the bottom up. And so, you can parameterize your ignorance of it simply by saying if you have a potential energy for a scalar field, for example, you better allow for the possibility that the inflaton couples to new light degrees of freedom that come in at a scale that you would think is, at most M Planck. And so that would give a rather random-looking potential like this, which would not be suitable for inflation. There's also this interesting issue that there's no such thing as a continuous global symmetry in quantum gravity, we think. But the way this works for string theory in axion directions and their many duals is much, much more regular than that. We have couplings between axions and fluxes, which give us a branch structure in the potential, on each branch of which the field range goes off to large values under the control of a very finely spaced discrete shift symmetry. The whole structure exhibits invariance under that discrete shift symmetry. And so, again, it's a much more regular picture than the straw man on the left. And it provides a rather simple, if you like, UV completion of the old idea of chaotic inflation of Linde, and with some residual effects that are still inherited from what you might call natural inflation of Friis et al. So it fits into this history rather nicely. Now, of course, as other speakers have already emphasized, inflation itself does not hinge on primordial B modes being detectable, but there's already a lot of evidence for it. The temperature power spectrum, along with the E mode polarization, provide a function's worth of evidence in favor of this paradigm, which gives a framework explaining why the perturbations should be approximately scale invariant. Matthias explained this very well and gave the plot. And although it's a very interesting question to ask for alternatives and to investigate the possibility of such alternatives, there isn't a known consistent alternative that, and by that I'm including what I would call a thought experimental constraint, that it be consistent with black hole thermodynamics, as well as giving a controlled description of the space-like singularity involved. That's a tall order, but it's necessary to make a claim about alternatives. So that's where we are. But what is really at stake instead of inflation itself is a genuine observational lever to quantum gravity. So, I personally don't care what the particular model of inflation is, except insofar as it has other implications. And again, there is a very interesting implication via this Lyth relation to the field range. So just quickly, if you haven't seen this, it's a very simple two-line argument. You take the expression for the number of e-foldings, integral dA over A, where A is the scale factor. You use the chain rule 3 times. You compute the 2-point function of tensors and scalar perturbations, and you take their ratio R, the famous R. I'm taking the slow roll assumption here. You pull these factors out of the integral, assuming things are slow roll inflation, therefore varying weakly, and you get this beautiful relation between the range of the field in Planck units and the tensor to scalar ratio R. So if you put in the numbers, you find, roughly speaking, and this depends on reheating issues and stuff, you can look at the snowmass documents, for example, for a recent discussion of exactly what it means. But the basic relation is between a field range of delta phi being bigger than m Planck and an observable tensor signal. So this, of course, implies sensitivity to an infinite sequence of Planck-suppressed operators if you just expand around some point in field space. The famous slow roll parameters, the ratio of the kinetic to potential energy, or v prime over v squared if you want, and eta, et cetera, would get order 1 corrections if you just wrote random terms here. So it's in the renormalization group sense, it's sensitive to an infinite sequence of dangerously irrelevant operators that are irrelevant but become important because the field varies over such a long range. So as was also explained earlier by Matthias, it's true that a shift symmetry, or an approximate shift symmetry that you can presume from the bottom up, gives radiative stability and even Wilsonian naturalness if you model build the scales to be exponentially small and some coupling. But still, it's a large assumption about the classical theory to put that in, and you have to wonder about the issue of global symmetries. And most people have enough curiosity to ask the question, to take seriously the requirement that this emerge from a well-defined theory of quantum gravity given this sensitivity. Okay, so of course, I don't really need to present this slide here. String theory is a good candidate for quantum gravity for many reasons. I've only listed a few here. It works out well with black hole thermodynamics. There are beautiful, theoretical relationships like ADS-CFT and string dualities that have been found, UV finiteness, some understanding of singularity resolutions, et cetera. And the intricate connections among different ingredients and limits in the theory that a lot of this conference is about. To me, that's quite related to the landscape, which is somewhat more controversial, but is our only current explanation for the cosmological constant. So we live in this interesting middle ground. There are a lot of solutions, but there's a lot of structure. Not everything goes. One aspect of that that's quite relevant here is that the axion decay constant is sub-Planckian in the controlled regions of the landscape we think we understand. There's no such thing as a hard cosmological constant that you can just put into the theory. If you go out to limits of moduli space, light degrees of freedom come down. We all know there are lots of interesting structural features of this theory. And so when it comes to this question, we have to sort out this middle ground between the many solutions and all this structure. So, of course, I'm biased, but I think this mechanism of monodromy answers these questions I think the theory answers this question in a very simple way with its various monodromy effects. So let me start with the case that I'll focus on in the talk, which is this effect for axions that come from the NSB field. So the basic couplings that are involved are these Stuckelberg-like couplings that we get from the squares of the generalized fluxes that we know and love in the theory. I'll write down the critical string type 2a and type 2b ones shortly. but they have this form of a regular field strength plus various axion wedge field strength terms. And it's that direct dependence on the axions times what become fluxes when you dimensionally reduce that gives this effect, that gives the fact that generically, quite generically, axion potentials in string theory are not periodic, but have this unwound feature. So here, for example, is D equals 10 type 2A. We know the fields and the field strengths. And because we'll be interested in this and also its T-dual, effective T-duals to 2B, let me highlight these terms like F naught B here and F naught B wedge B in the generalized field strength F tilde 4 in type 2A. So if you reduce this on a circle, you have to expect effective T-duals of these terms, including the ones that will come from, say, this B wedge B times some flux squared in the action. So that gives us, in the low energy theory, a potential that includes a fiducial quartic potential, but coupled to moduli and all the other degrees of freedom that we need to deal with. But that's going to be one of the themes when it comes to the question of the range of R that we obtain. Okay, so this is the basic picture. We have these F tilde squares. They give fluxes times B to some power N squared. And so there's some fiducial power in this potential that I've called 2N here, which I'll generally call P0. And in any given example, the ultimate behavior of the potential is not this P0 power law generally. It's often a power law, but with a reduced power. So we've seen many examples of, for example, final reduced powers coming from the adjustments of other fields, including the linear potential and the phi to the 2/3 and so on, and now we've generalized that. Okay, so corrections to this are interestingly automatically suppressed by extra powers of G. So the corrections that I've listed here, let me say, which we should always ask about. What would be alpha prime-like corrections, which are still tree-level couplings of the Ramon field strengths, come in the frame that is standard to work in, which I'm working in. They come with extra powers of the string coupling G, as is was famously discovered during the duality revolution. And they usually also come with extra suppressions from the fluxes diluting. So when you get into the details, you find that this is a good thing. It suppresses these corrections enough to mean that indeed we can focus on the F tilde squared terms. And in general, for control, we of course work at large-ish radii. So we are up at high scales, and the radii can't be parametrically large, but they turn out to be factors of 10 or something, which is arguably sufficient, and weak coupling. And of course, we can do that with or without low-energy supersymmetry, which is an orthogonal question. So of course, these monodromies are common in the theory generally. Complex structure moduli, just the tau of a torus. If you move in that direction without any fluxes, of course, you come back to the same torus. But if you put a flux in, then you don't. So that's the dumbest example of monodromy. And of course, this kind of thing has been studied a lot in Calabi-Yau geometries. So let me continue with the schematic description a few steps further. We have a structure for the potential that is some function of the moduli like we usually talk about independently of inflation. Then we have moduli-dependent inflaton potential terms like this one I've written here with these powers of the inflaton appearing directly, or the powers of the axion appearing directly. Again, the whole structure is totally periodic, but on a given branch with fixed fluxes, it is not. It's a large field potential. But the brane spectrum, for example, wrapped on those the cycles that give us the axions by integrating the B potential field. So again, little b here is the integral of the NSB field. Branes wrapping on that cycle have a spectrum that is periodic. So a lot of the physics is controlled by that underlying periodicity. And so on each branch, we have a large range. And it is cut off by something. Of course, we're up at high scales, and you can't go on forever. So you cut it off at the scale where some modulus goes unstable, or ultimately at the string scale, which is a lot, again, like Linde's original picture of chaotic inflation where you shut up about it up at the Planck scale. This is just a more nuanced version of that. Okay, so we have moduli dependence here, here, and also in the kinetic term. And it's not a surprise that we often find these powers I alluded to earlier that are lower than the fiducial power, and it's basically because the moduli fields adjust in an energetically favorable way. Of course, that can mean they just go unstable, but when they don't, they tend to flatten out the potential relative to the fiducial power. The kinetic term also comes in, and of course, one canonically normalizes the field in this way. And a simple example to keep in mind without any special features is just sort of a one-scale model where the canonical field in Planck units is this axion little b over the size L squared of the space that it wraps, or the whole space if it's a one-scale situation. Okay, so I've kind of already said this. I've now expressed it again in the language of the canonical field. So in specific models, we do find what I was describing, that there's some fiducial power P0 coming from those b to the n terms, that the moduli couple to that and adjust. For example, the inflationary potential can help stabilize the moduli during the process very easily. And that leads to some behavior like this. And I'll give you very simple examples shortly where the overall trend of the potential is some phi to the p, where p is generally not an integer, it's some rational value. Again, generically lower than this P0. And then plus, there will be a residual oscillatory contribution that's quite model dependent. So it comes, for example, from instantons, which can be non-perturbably suppressed, but on the high end of that, it's actually potentially detectable, so we'll come back to that. Okay, so these are the powers that we've been finding. We originally found these two powers, although this model has a problem in the moduli stabilization part of it, although in our recent paper we found another example that gave 2/3, so whatever, it's all still in there. The linear potential has been studied extensively, but now we find a broader range, as I say. So I said this before, but let me just give you a little more intuition for it. We're familiar with fluxes helping stabilize certain moduli, and it's kind of a two-term structure where on a given cycle in its dual, a flux on the first cycle wants it to expand, the flux on the dual cycle wants that to expand, so they play off each other, and the ratio of the two sizes gets stabilized. What happens here is during inflation, it's quite easy for the b times q, the b times flux piece, to play the role of the original flux and do part of that job. So this ratio of length scales I wrote schematically here gets stabilized by that effect, where instead of just a pure flux, we can consider the axion potential energy component, which behaves a lot like a flux because it came from that generalized f tilde squared thing. So that's why in retrospect, that's why we found these interesting non-analytic powers out of a theory that has analytic terms in the Lagrangian. So the P0 can be 2 or 4, for example, and then we find the interesting list of powers I explained after finishing the job. So in particular, that specific linear model, which also has a brane description that makes it patently obvious why it gave a linear potential, can be understood also in that framework using ADS-CFT and using the flux and gravity description. So it all fits together in a unified way, I would say. Now, of course, this is not the most generic thing. There might be other mechanisms, first of all, but even with this one, you can take into account that there are lots of axion fields, and maybe more of them participate. So you can, trivially work out the phenomenology of that, and it tends to shift the tilt redder, simply because each axion lives on a steeper part of its individual potential. Okay. So sorry if this is a little too small, but here I've written the relevant flux squared and generalized flux squared terms in type 2A, and then the ones in our recent paper with McAllister, Westphal race that we use in these models, which are essentially T-duals of that B naught, F naught, V wedge B squared thing I mentioned earlier. So we can exhibit the basic effect I'm talking about in a simple example with just a silly torus compactification where we distribute the fluxes and the axions in the way I've written here. And the basic effect of this, what I keep describing in terms of moduli stabilization and flattening is you can capture here. So there's some ratio scales U that in this toroidal model enter into the potential in this way. There's the quartic term that came from the F B wedge B squared. There's some fluxes that, in the absence of the inflation, would stabilize this modulus U, which is just a ratio of lengths of the torus. And okay, you can see that during inflation, this and that can balance each other. And when they do, this is a trivial algebra line here to solve for U in terms of B. Plug it back in, and you see immediately that the effective potential after you do that, which is to say consistently solve for the moduli dynamics in this trivial example, is that instead of a quartic potential, we flatten to a cubic. So P naught equals 4, P equals 3, and what I just described. And I'm kind of embarrassed not to have thought about these higher B wedge B terms in the past, and the bicep announcement immediately triggered this possibility, for better or worse. And this is actually 0.2, but we'll see. Okay, so one checks that the kinetic terms are in fact negligible. We're talking about a complex structure modulus moving during the process. Does it go to some extreme value? No. And the asymmetric directions, which I didn't really talk about, are okay. Okay, so we made a point of giving, as we like to do, a proof of principle of this in some really more complete scenario for moduli stabilization, in this case using a simple product of Riemann surfaces that Alex Saltman and I stabilized some years ago, which I think is quite fitting for this kind of physics, which is high scale. And as you might imagine, it fits well with the toy model I gave earlier with that silly torus, generalizing that in a way that's not too complicated. The basic mechanism here is extremely simple. The complications that there are in the whole thing, I think, come from the, of course, important part of moduli stabilization. So in this case, in our recent cases, we did this for Riemann surface compactifications, and got these powers once again. So I'm not going to go through the details. We insist on solving the obvious microphysical constraints that the various ingredients are consistent with each other. So the axions we turn on needed to be consistent with the ingredients Saltman and I had originally used, et cetera. The stabilization mechanism involved a 3-term structure for one combination of the dilaton and volume and a 2-term for the other. And basically in the same sort of way that I was describing earlier, depending on how we distributed fluxes and B's to get flux quanta and axions, we get different behaviors, different detailed behaviors for the potential, and that's in this recent paper, but I certainly can't explain it all here. Okay, so where are we observationally? Of course, we heard the status. This is where we were with WMAP. This is Planck, and this is the fiducial bicep with running included, so I didn't put any of the dots on that plot. And it's really our job as theorists to figure out better what the right theoretical blob is to put on this kind of picture. I'm not sure that there's a continuum of values of R and NS. We're used to more of a discretuum in our string theory landscape at most, and there could be interesting theorems just based on the structure of these flux axion couplings that might give us lists of these rational powers and or ranges of this power and hence the phenomenological output. So I think it's a big opportunity, and I don't think this plane is populated continuously. I don't think we know, and it's interesting to figure it out. If one does, there's been interesting papers post-bicep sort of trying to hone in on exactly how well one will end up being able to do in distinguishing things. Okay, so there are lots of axions in the theory. I focused on B. There's, of course, also the Ramon ones. There's the complex structures. There's brane positions, which can behave like pseudo-axions, et cetera. There are a lot of them. I think, as far as I can tell, they're over half the scalar fields. If you assume low energy SUSY, they're half the fields basically. If you don't, their number just proliferates. For example, in high dimensions, They just completely dominate the spectrum. So in my view, it was definitely a myth when people kept saying string theory prefers small r, but there's some exotic possibilities that generate r. I don't think there's any credible argument for that I've heard. If you have one, let me know. And I think this is getting very serious observationally. I think we should be careful about making such statements. I don't think we know. I think it's a very interesting question. Is there a useful theoretical prior on R in string theory? The mechanisms that generate one kind or the other are quite different as far as we know so far. So there might be room for progress on this. But again, this was an oft-quoted statement that I've never understood. OK, one fun thing we're playing with now is, in fact, going up in dimension just to poke at this and see how high the powers, fiducial powers can get, and how the flattening reduces it down, and how big a range are we going to end up with the final power p. So that's in progress with these guys. And one more thing that we are working on actively now with Flauger, McAllister, and Westphal. By the way, Flauger did a reanalysis of the linear model of axion monodromy some years ago, and luckily it survived. But okay. So in this study, what we need to do is produce templates for searching in the CMB. I mean now the Planck data, basically, for this probably long shot, but very interesting possibility of these residual oscillations. And there's been a lot of interesting work on this already, including from folks here at the Planck collaboration, et cetera. But what's challenging about it actually is that the period f depends on moduli like everything else does. And these drifts in moduli that I was talking about also affect this f. And it's enough that you can lose the signal if you don't use the right template. And so, it's a fun data analysis and theory problem to do our best at estimating how to do this most accurately. And so, again, as I said, it can easily wash out, but we can, use our best understanding of these things, such as the pattern we saw with these powers p here translates, at least in those examples or classes of examples, to powers here and here, in particular inside this cosine. And maybe we can scan over this p tilde 2 power here, for example, as well as the frequency. So that's in the works. Okay, so in however many months it takes for the game to conclude, it will be interesting to see whether we have 5 sigma evidence, which is 3.5 million to 1 in the World Cup analogy. And it's going to be exciting either way. I think Matthias made that point very clearly already. Because either way, we learn something about inflation and the role or not of large field ranges in a very clean way. This is a threshold. This is not a fishing expedition. It's a real threshold. It's an unprecedented lever to quantum gravity in string theory that's observationally in great shape because of these multiple experiments that we have been talking about. And I hope we can do a bit better as theorists to develop a more systematic understanding of these things, in the case of monodromy, based on the structure of the flux axion coupling. So let me stop there.
Any questions? Yes, Paul.
First of all, given what I said, I'm obliged to ask you what you're assuming about initial conditions and what you're assuming about the multiverse in making your predictions.
Okay.
But the real question I wanted to ask you was this. Models you've shown, and it's true of a lot of the string-inspired models, are extremely complicated and ugly from the point of view, at least that appear that way in terms of the number, the constructions. And we're trying to explain a very simple universe. Is it your belief that in order to make string theory compatible with this very simple universe, we're forced to such complex constructions?
I think what complexity there is, as I was trying to explain, although I had to go through it too quickly, is in the moduli stabilization part of the problem. I think this mechanism for large field inflation is extremely simple. It threads through these various requirements of being consistent with quantum gravity without assuming an underlying global symmetry, in a way that, to me, is one of the nice mathematical things that string theory led us to. It's got, again, this shift symmetry that's very finely spaced, so it's enough of a symmetry to do the job, and it's very simple in itself, the mechanism. And it's, again, these axions and these fluxes are all over the place in the theory. Now, it is complicated to do these proofs of principle, which include, at least plausible stabilization mechanisms for all the moduli fields. And that's where it does get complicated. And I view that as, and this is, it's a matter of opinion, but I view that as connected more to the cosmological constant at late times, the fact that we need, some mechanism for explaining that, and the only viable one anyone's proposed is, Weinberg et al.'s old one, which string theory seems to fit with via the complication of all the solutions. So the inflationary mechanism itself is really very simple. The moduli stabilization, has some essential complications, and I think probably for good reasons. When it comes to the initial conditions, it's funny because I agree with you that there are very interesting theoretical problems there, which to me is part of why this subject is so interesting. It has some kind of tie to that. But for the phenomenology, you don't need to go there. And as far as the initial conditions go, for high field inflation, the patch is relatively small. You basically need a factor of 10, assuming you don't have a factor of 10 input into your initial conditions to avoid having too high an energy density. So for inflation to get going, as you know very well, you need the potential energy to dominate over other sources, but you don't need it by much. And particularly at high scale. And by the way, I've been a fan of large field inflation before I worked on it, and it was basically for this reason that it's you do need some factor of 10 or something to get going, but that's for the phenomenological range, that's what you need. And as for why you start up on the potential instead of down, I mean, it's fine. You start up on the potential to model the world. I don't. Oh, you think you understand the measure?
I think I understand statistical mechanical measures enough to say that there's an argument against them being likely. I don't know any counter argument at present.
I know lots of arguments that go both ways, and none of them are compelling. So maybe we can talk about the phenomenology more.
Since time is ticking, maybe one more.
By statistical mechanics, we should exclude Big Bang nucleosynthesis as a good theory of the early universe, since it starts with lower entropy than it ends up with.
Well, maybe we should continue on that later. And that's, thank Eva.